let me start the idea StatiCa and our module connection. And I will create a new project. So let's start with the input of a new project. Where I set the code, the Eurocode and the S275 material, and I will use this 3D frame topology from a wizard, which can help me to speed up the input of the geometry. And I will use this first topology of the column and two connected beams. Now the new project is in creating, so let's wait a while for that. And I will continue with the setting of the geometry to define the required shape of the connection. So first of all, I will change the length of the column, and I will also modify the cross section. So for this column, I will use a general cross-section tool to model a cross section from I section. So for that I will input a new part of that. It's HEB 600, and I will also add another part of that. That will be let's say T sections. Which will be a part of HEB 500. To put it into a correct position, I just need to select the master component and the insert point, and I will also set the rotation and the shift of this segment. Now I can just copy this existing part and put it on the second side or other side of the section. So now you see that I have defined this general cross section, and the model was updated, and we can see this section on the column. Now let's continue with this B1 as a part of the rafter. So I will select this member from a list, and here I will again change the cross section. So I will use HEB 280, and I will change the slope because it's a part of a roof, and I will also define a second beam by inputting of a new member and modification of this properties. So let's rotate it and change the slope to plus 6 degrees. So now we have the rafter. Now let's adapt this let's say purlin, and I will use the cross section HEB or HEA, sorry, 180, and I will set the rotation of the section to put it into the plane of the roof. The last member which I'm going to add is a bracing member. So here let's again change the section to L profile 108, and I will adapt the position to put it into required shape. So now, as you see, I have defined the geometry of our connection. We have all necessary members, and now let's continue with the input of the load effects. So I will select the load effects in the navigator, and I will define the values of the internal forces or the load effects which are acting on the beams. So first of all, let's put here a shear force on the rafter. Minus 50 and 90. I will also, you can see that these load effects are graphically displayed in the 3D view. Here I made a small mistake, and I will also add a shear force on a purlin and the normal force on a bracing bar. So that's the input of the load effects. As you see, I have the possibility to define more sets of the load effects, and this example I will use just this one. Now let's design the connection of all members. So for that I will use the manufacturing operations. The first of them is a cut of a member, which enables me to extend the existing column with some offset, because I would like to have some space for the connecting of another members. The another operation is the end plate to connect the member of the rafters. Now I just will select some default grade and the size of the bolts. Okay, so let's select a member M4. And I will see that the end plate was added, and I will change the properties. For example, the thickness of the plate, the dimensions of the offsets. I will set the profile from the symmetrical because I would like to have a different offsets to the top and the bottom. And I will also rearrange the bolts. So let's put here the minus 40 and the bolts at the bottom part. Sorry, minus 60, 50 and 100. 20, and let's also set the offset to the right to minus 40. So now you see that I have defined these bolts to connect the member, and finally I will change the size of the welds to 4 millimeters. So that's the input of this end plate. Now I can copy this input and apply it on another beam of the rafter. So let's copy this operation, and I will select the member B1. So my end plate was also added on this member, and I will just change some properties like bottom offset to have enough space for the connecting of the bracing member, and I will also add another row of the bolts. Now let's connect the purlin, the member B2. And for that I will define an operation fin plate. So let's select the member B2. I will change the thickness of the connecting plate and the offsets of the plate. Maybe I will also change the location to the rear, just to make it visible for us. And finally, I will change the size of the bolts to 12 millimeters. So that's about the connecting of the purlin. And the last operation which we need to define is for the connection of the bracing bar. For that I will use the gusset plate. So let's select a member M5, and I will connect it to member B1 and the plate EP2, that's the second end plate. So now you see that a new connecting plate is applied. Now we just need to change some, again, the properties to put it into a correct shape. So I will enlarge the connecting plate. I will set the alignment to rear and the type to bolted. Here, and as you see, I can change the size of the welds and type of to connect this this plate, and I will also rearrange the bolts. I will put another bolt, and I will change the size to 60 millimeters. So now we have connected the diagonal, and the last step which I wanted to do is to cut a corner of the plate. So to that I can use the editor. Select the corner number 2, and I will put the required dimensions of the cut. Okay. So as you see, the plate was cutted, and we have modeled the all necessary connections of our joint. So now I will just change or adapt the input of the load, because as you see here we have a hinged connection of the purlin. So for that I'm going to back to the load effects, and I will select the member B2, and I will put the position of the shear force which is acting on the member, and now you see that I have defined a hinge into position of the bolts of the real position of the hinge on the purlin. So that's it. That's the input of our connection, and we can continue with a check of all parts. So let's go to the check in the navigator, and I will start the analysis. Now a nonlinear analysis is started. As you will see, we calculate some set of iterations because we take into account a nonlinear behavior of the material, and we will wait a while for the results. Then I will show you the available results, which we can see in the top ribbon. Yeah, so you can go through the available results and graphically see them in the 3D window. So for example, the first of them is this overall check with traffic lights, which can really help us to identify the critical parts of the connections. So for example, as you see in gray are the unused or small usage of the components or the plates. We have the green color, which represents the let's say the standard usage. The orange means that we are really near to the limit of the checks, and we can also have the red one for the parts which are over the limits. If we would like to go to the more detailed checks, we can, for example, see the strain check. That's useful for the control of all plates in the structure, or we can see the equivalent stresses in the 3D window, plane strain, and so on. If you would like to go through the detailed results, so for that we provide these tables for the plates, bolts, and welds with detailed values. So for example, maybe let me mention the group of bolts. If I go back to the overall check, you can very easily identify, for example, this bolt, which is in orange, and it's automatically highlighted in the table, and we see that here we have the 97.5% of the utilization intention. So then you can really see and identify the critical parts of the connection. The last point I would like to show is the output report. We have 3 levels: one line, a report, which is very brief output, only we can see overview of the values of all checks, or one page output, or if you need more detailed report, then you can set the content by these checkboxes. So, for example, I can add the bill of material or drawings and so on. So maybe let me refresh this output report, and let's wait a while for that, and we can see what is inside a report. So, for example, you can see here the summary of the beams, the cross sections, of course, all bolts, load effects, everything what was defined in the project, the results, again the tables for the detailed checks of bolts, welds, the manufacturing operations, and because I did the bill of material, we can also see these drawings of all plates, and finally, for example, the summary of the code settings which was used in our project. So that was the stress-strain analysis of this connection. I would like to also show you the possibility of the calculation of the stiffness. So here I will change the type of the analysis to a stiffness. Now let me select just the member M4 which I would like to analyze. So I will set it as an analyzed member, and we can calculate the stiffness of the connection of this member. So let's go back to the check, and I will start the analysis. Now we need to again wait a little small while for the results. In this case we need more calculations because we are providing and calculating the real, let's say, working diagram of the connection. Here I would like to mention that you can find more about the theory in our resource center, which is available on our web page. So if I go to the group of the steel, then here in the theoretical background you can find the part about the stiffness analysis, when we describe the theory and all available values which are in the chart. Now we have the results in our example. So as you see in our example, the connection is semi-rigid. We can see the real working diagram of our connection, the level of the load on our beam, and also the classification for a rigid joint, pinned joint, and the real value of our stiffness, which you can use in your original 3D model. Now let me continue with the second example, and that's a demonstration of the link with the advanced steel. Here you can see some steel structure, and I will export it and check this top connection on the frame. So to that I need to start our link by a command concheck, which is implemented directly into the advanced steel. Now we just need to select a node of the connection, the connected members, and finally the components of the connection, like bolts, welds, and the plates. So when I finish this, the geometry is exported into StatiCa Connection automatically in background, and a new project of StatiCa is created. So let's now the new idea StatiCa Connection is launching with this new project from the advanced deal. So let's again, we need to wait a while for this. Okay, so now we can see that this project, and if you can compare, then we have the same, let's say the same topology, the same shape, which we have also here in the advanced deal. So now let's finish the design of this connection. So for that, as you see, I don't need to model the members, which were automatically imported, and also the operations, the plates and or components of the connection. We just need to define the set of the load. So for that, I will create a new set of the load effects. For this, I can use also the possibility to import the load from the Excel sheet. So you can, for example, have some set of the internal forces in the Excel, and for that I will just use this option to import. And as you see, all forces were automatically added. I just need to define now again the position of the load, in our case for the purlins. So let's put here 60 millimeters, and we can go directly to the check of the structure. So I will calculate it. So let's wait a while for this. Yes, and as you see that we can obtain a really fast check of the connection, which was modeled in the advanced deal. Again, we have the same set of the results, so overall check, all values in the tables, and we can really go into the deep analysis of this connection. So that was the second example which I wanted to demonstrate, and now we will continue with another examples, and I will give a presenter to my colleague Philip.
So good afternoon also from me, and I will show you an easy example of tubed connection. So let me start from scratch in idea StatiCa Connection. Let's run a new project under an AISC code with basic A36 material, and I will select the 3D frame topology to start with, and I will start with let's say this one. So some predefined geometry is loaded, and let's adjust it a little bit. So for example, I will change the cross section of the CH member to the pipe cross section in imperial units, and it will be 12 XS. So it is updated. Let's change the length of, pardon, I will switch my units. So to show you that, let's go to the File, Units, and I will select the button Default Imperial. And I can now easily input everything in, for example, inches. So the length will be 30 inches. It will be the ended type. General, and I will rotate it to the opposite side and also shift it a little bit to -9 inches. I will also change some properties for diagonals. So this one will be actually the pipe 6 STD. So let's find it out. Okay. And I also need to angle, so to rotate the angle a little bit to 60 degrees and move it a little bit upwards to 1.875 inch. Also some changes for diagonal number 2. It will be also the pipe, and this pipe will be 10 inches STD. Also I need to adjust the bracing, and this one will be the last type, which is pipe 6 STD. Okay, and I will also add one more member to connect to. So I will click on add a new member, which will be exactly the same as the CH cross section. So the 12XS, it's already there, and we need just to input the length of 11 inches, switch direction to 0 degrees and move it by 9 inches. So I have defined the geometry. Now let's move to the load effect. And as it has been mentioned, I can easily copy these internal forces. So let me just open the Excel file, copy the internal forces, and import them in easy way. Also one note that I will work under AISC design code, and I need to switch on the check of the equilibrium. To study details about this issue, you can look into our tutorial or theoretical background. So after switching it on, I will import the real forces, and they are here. As you can see, everything is balanced as it should be in the joints, and we can proceed to the design tab, where I will define several manufacturing operations. So at first I will connect the CH member with M5 member, and to do that I will choose plate-to-plate connection. From bolt assembly I will stay with A490, and the size will be 1 1/8 of inch. Okay, I will connect member CH with M5 as I mentioned. I will change the thickness to be 1 inch of each plate, and to actually be a circled plate with a radius of 10 inches, and we want to add a hole into it, so inner radius will be 5.875. So as you can see, it's hollow. The type of bolts has been already selected. Let's just move them a little bit to the edges. So the radius for bolts will be 8.25 inches, and I will adjust the number of bolts, which will be 12. And let's change the weld size and material. So I will adjust it to 0.375 inches, also the second one, and I will choose material to be E100 in both cases, and we can continue with connection of the diagonals. To connect the diagonals, I will use the cut operation, which will cut the member, for example, D2 at first, cut by CH member, and I will select the cutting method as a surface. As you can see, it's cut it by this member, and we need just to define the size of welds and so on. So to speed this up, I will define it on 3/8 of an inch, and also raise a little bit the material. Now the diagonal D2 is connected, and we need to cut the diagonal D1 by member CH and also by the member D2. So for example, to speed this process, I can use the copy operation. Let's just switch to the member D1. I can, for example, make a little smaller welds. So I will just adjust these options. And I can, for example, change the material. Now, let's say I can copy it once more, and I will cut the diagonal D1 by the diagonal D2. And I can, for example, use another type of welds. And to finish the design process, I will cut also the bracing, which I will show you. So I will cut the V member by CH member, also the surface cutting method with a 1/4 inch of size of welds with E80 type. And one more thing before I will run the analysis, and it's the matter of code setup to switch from elastic behavior of welds to the plastic redistribution. After clicking OK, we can proceed to the check tab and run nonlinear analysis. And after a few seconds, we should be able to see the results. Okay, so now you can see on the traffic light that almost everything is in optimal design, and these 3 bolts are utilized between 95 and 100%, so they are orange one. I don't want to go into more details about the results as they have been mentioned previously, so if you have more questions, we will answer them in the end, and I will continue with last example, which will be imported from SAP 2000. So I'm currently working with the latest version 19, and this is some basic structure which we want to import. So we already added the plugin directly in SAP 2000, and to work with it you need to define the point and connected members. After that, I can just run the plugin and our wizard will show. So let's work under European code. You can adjust its name. I will stay with the default. You can adjust which member should be bearing, continuous, and so on. I think all these properties you can adjust even in IDEA later. So I can go into the connection design, which will run our software. As you can see, we have already all geometry, all the cross sections, and even all the load effects and combinations, several of them. To do this joint, I will not just need to elongate a little bit these diagonals. So let's stay with 500 millimeters, and I can easily make a design. And what I wanted to show you there is how efficient it's to work with the templates. So I already created a template on this type of connection before, so I can just easily go into apply the template, and you can see that it's already there. After clicking on apply, everything is designed in a matter of a second or two. or you can easily just adjust few things. Yes, so for example, switching the type of bolts and so on. You can do several templates also, so you will make manufacturing operations and then just save this as template, or create a template and you should be able to work with them in a list of templates. They will be shown for your topology. So we have geometry, load effects, and apply the template for design. We can proceed to the check and run the calculation. It should be also very quick, although we have several combinations there, so the solver will go through all of them. So it will take a little while, as you can see on progress bar. And after a few seconds, let's wait. Okay, so you can see, for example, equivalent stress in all the plates. For example, I want to click on this plate, it will be shown in the 2D scene. I can easily see the results and so on. So I think that was everything from my side. Maybe we can continue to the questions, and I will maybe return the presenter to Juraj.
Thank you very much, Philip. Before we dig into the questions, quick information about what is after the webinar. Kindly fill out a short survey, no more than 30 seconds, just a couple of questions. We will prepare the recording and send it on Friday. And we encourage you to test our trial. You can easily request it at our website or indicate it in the survey. When you're at our website, you just can go directly, start your 14-day trial, and we will deliver that. As Martin showed, we have a resource center with all the materials. And if you want to know who is already using the software, you can go to testimonials section and see what engineers from all around the world are saying about using this in their projects in many countries. Okay, now let's jump into questions. Well,
so maybe the first question what we had was about the preloaded bolts. So here I would ask Philip if he can show us this option.
Yes, definitely I can. So let me just start sharing of my screen. I hope you see it. So for example, in this case, I will show you it on a plastic strain. So as you can see, these plates are loaded with the shears and so on from bolts, because the bolts are bearing shear force in interaction. And to make preloaded bolts from them, I will select the friction type in shear force transfer in a grid or in any bolts input, and by that I will run also the calculation. After a few seconds I will show you that all the shear force is transported by the friction, and thereby the utilization of the plate should be a little smaller. As you can see, we had the bolts, for example these orange ones, almost to the 100% of utilization. Now they had just around 87. To demonstrate, under plastic strain it's less stressed, and also the tab for bolts has been switched or added as preloaded bolts, and we are checking the slip resistance of the bolts. Yes. Maybe another question?
Yeah, now I will go through some another questions. Aha, když nejsou presenter, tak mě neslyšíte? Pořádně neslyšíte, jo? Yeah. So I will go through another questions. We received some another questions. So for example, about if there is a possibility of the modeling of a connection between steel structure or steel members and the concrete members. So here I would like to mention and invite you to next webinar, which will be dedicated to this topic, when we will demonstrate the possibilities of the footing and anchoring. So we have the possibility to model this type of the connection as well. The next question was about the AISC standards. So here we had already demonstrated that example with tubes, which was modeled in the American code and as well in units. So maybe we forgot just to mention this. So yes, we can model and analyze the connections with in the American code. Then let me check the list what we have also here. There is another question about the bent plate. So we can model this. We have the possibility to define a new section, or let's say, or the cross-section type. Maybe just let me, sorry, I have no the example prepared for this, but I will just show you this possibility, what we can do. So just let me share it. So I will share my screen. So here we have some very simple topology. But what I wanted to demonstrate is this cross-section type. So if I'll go to the cold formed sections, so here I can mention that we have a library for cold formed sections, and one of them is this bented profile, and I can also define the angle between the plates. Yeah? So I can, for example, have this sharp shape, or very sharp one, or we can go to, for example, the open shape. So as you see, you can play with the shape of the bented plate, and this provides you the possibility to model this type of the plates. Now I have defined that as a member, as a start done part of that, but you can also define that as a connecting plate or part of the section by the operational stiffening member. Okay. Then what we have another questions about the API. Yes, we provide the open API to our StatiCa Connection. So if you are interested, you can contact us, and we can provide you the necessary informations about this. We are also this mention is in our resource center in this group open model. So we call it StatiCa Open Model (IOM). When it's described here. In general, you are able to create the cross section or the model directly from the outside of our application, and you can just use it as for the analysis. Another question is if I can explain the setup of the code setup of the model. So yes, we have this possibility in the check group. We have this group for the code setup, and you can see that you can define some values which are for the correct setting of the analysis. One of them is also the definition, for example, of the mesh. So you can here define, for example, the number of the mesh of the elements, on the edge of some members. In fact, I think that these default values are optimized for the correct analysis. If you, for example, need some detailing or some of the mesh, you can increase these numbers. Another question is, I will read it. Based on what I saw, all the analyses were non-linear. Can you please show us a linear analysis based on the Eurocode? We don't have the linear analysis. Yeah, that's quite important to understand that all our model is the non-linear. We take into the account non-linear behavior of the plates, because we check all parts. That means that the plates and parts of the members to the plastic strain. So to calculate the correct plastic strain, we need to take into the account the non-linear behavior of the material. And then we have another example question. What we have? Could we export a detail from AutoCAD with the full pro structures? So here I'm not sure what the user what the attendee mean by the pro structure. Maybe I will just summarize or explain the general link. So we are able to export from the advanced steel. It's not from the AutoCAD, but from the advanced steel. The modeled connections. Yeah, so if you model any connection in advanced steel, we can export it into our StatiCa connection. Is there extension for etaps? So the etaps is in our scope. Yeah, so we have some plans to link to etaps this year, so we expect it let's say in the version 8.1, which will be released during the autumn in this year. Yes, but if we can, the other question is if we can make the 3D model for the full structure in IDEA. Our module StatiCa Connection is dedicated for the connections only. So you can model only connections here. We have also some another modules. If I show what we have in the steel, we have also the module beam and the column. So it's not about under frame 2D. So there is a possibility to model some parts of the structures. But I would say that it is not a full 3D, let's say, general model of the structure. And another question, do you have a plugin for SIA engineer to export the forces as in the same as the plugin for the SAP 2000? So we are implementing this a new link with SIA Engineer in the May, which so it will be a part of a new release of StatiCa 8.0. So this is something that is in the development now. For the other questions, for the UK practice design to Eurocode, is there any links to the SCI green books guides? Yes, we have a set of the verifications, and which was also created by our local partner in the UK, and so we can provide a link to this. The other question is that we are looking for the StatPro compatibility or the link. Yes, this is something also in the development. We are going to release in the version 8.0. Another question, does the base plate with anchor bolts shall be verified? Yes, we can check and design the footing and anchoring as well. In our StatiCa Connection, we have a special, maybe just to mention, we have a special operation for this. So we have the operation base plate, which enables to model this type of the connections. Maybe I can just create, or just to show you this option. So I will create a new one. So as you see, we have a wizard for the anchoring. So we can, for example, just to select the first option, the simple one. So as you see, we can model the footing of a column. It could be more general, so there could be some diagonals and so on, and it could be also to the column.